We want to define the inverses of the trigonometric functions. We're first going to do this with sine, with y equals sine x. Now I've put the graph of y equals sine x up on the left side of the screen, and as you can see, since these actually go on forever in both directions, we know that the sine function simply repeats itself uh, you know, forever in both directions. Recall the horizontal line test tells us whether a function is one-to-one and therefore whether it is invertible. So we can easily see the sine function fails the horizontal line test because a horizontal line intersects the function in more than one point. So it would seem as if we can't define an inverse for a trigonometric function like sine, but it turns out that we can. What we're going to do is we're going to restrict its domain in sort of a natural way. If you look at just the middle of this function, what you can see is that if I were to stop the function right there and right there, then I actually get, let me make this line a little thicker just for that part, then in between those two green dots I have a little piece of a function that does in fact satisfy the horizontal line test. Just the thick purple part here, clearly the horizontal line only intersects that part of the function in one point. So what I'm going to do is I'm going to redraw the sine function with just its restricted domain, like this. And we'll see, is that, there we go, I'll keep it in a thick line so it looks like that. That is the sine function with its domain restricted to negative pi over 2 to pi over 2. So this is y equals sine x for the domain negative pi over 2 is less than or equal to x is less than or equal to pi over 2. Sorry, not negative pi over 2, pi over 2 on that side. Okay, so now we have, having restricted the domain, we do have a one-to-one function, and it is invertible. So what we can do is we can define its inverse function as the following. So the inverse of y equals sine x on the restricted domain negative pi over 2 to pi over 2, let me write that a little neater. The inverse of the sine function on that restricted domain is a different function called y equals arcsine of x. Now I know, by the way, that this word doesn't look anything like arcsine of x. We sometimes write it out this way as either arcsine x or arcsine x. There's a technical distinction between using capital A and lowercase a in this case. I don't want to make a big deal of it. Since we're already asserting that this is a function, our textbook seems to use these more or less interchangeably, and I don't want to make a big deal of whether it's capital A or lowercase a. So normally, actually, I'm just going to use this terminology that you see here. Sometimes I will use either of these and to mean the exact same thing. In other words, the inverse function of y equals sine x on a restricted domain. Just realize that when I write it this way, sine with a -1 up there, I'm not saying take the reciprocal of the sine function, which is cosecant. I'm saying take the inverse function of the restricted sine function, and you do pronounce it, even when it's written that way, you do pronounce it as arcsine. Okay, so what are the properties of the arcsine function? Well, first of all, if y is equal to sine x, then, and I should point out where 0 is not 0, where negative pi over 2 is less than or equal to x is less than or equal to pi over 2, then x is equal to sine of y. Okay, so let's just consider what the properties of the arcsine function are. So first thing to note is what's written here on the left. If y equals the arcsine of x, then y is an angle. It's an angle specifically in this interval whose sine is x. This is something that I can't overstate, because many people assume that because the arcsine function looks, when you write it, a little bit like the sine function, they assume that because sine is just a number, that arcsine must also be a number. But no, With sine, the input to the sine function is an angle and its output is a number. Since arcsine is its inverse, the input to the sine function is a number, specifically a number in the interval -1 to 1, and what it gives you is an angle. It gives you an angle in the interval -π/2 to π/2. Since y is an angle, you expect it to be measured in radians. Okay, we'll see how that works shortly. It's really just a thing to remember that you're measuring an angle when you talk about the arcsine of a number. Okay, so let's draw a triangle where theta equals arcsine of 2x plus 1. Now, I put this in here specifically because most people just don't expect to see theta equals sine or cosine of anything. And I'm trying to emphasize that sine, arcsine, arccosine, arctangent, these are not the same thing as sine tangent, as sine, cosine, and tangent. They are angles. So if we draw an angle a triangle where theta equals the arcsine of 2x plus 1, what we're looking for is a triangle where sine of theta is equal to 2x plus 1. It's going to be a little more easier to see if I write this as a ratio. I know that this doesn't change anything algebraically, but if I say sine theta is equal to 2x plus 1 over 1, knowing that sine is opposite over hypotenuse, you can see how to write the triangle. The triangle, we have a right triangle, and we know that theta is an angle whose sine is 2x plus 1. That means that the opposite side is 2x plus 1, and the hypotenuse is 1. That is certainly a triangle where the sine, such that the sine of theta is 2x plus 1. Using the Pythagorean theorem, we can get the third leg here, which is 1 minus 2x plus 1 squared. And there's a triangle where theta equals arcsine of 2x plus 1. Okay, next problem. Let's evaluate arcsine of sine of pi over 6. Now, I put in here what the answer is. The answer is pi over 6, but it would be a mistake to assume that you can simply read the answer off just because arcsine and sine are inverse functions of each other, and I'm going to show you why. Let's work from the inside out. We know is that sine of pi over 6 is equal to 1/2. So that means that the arcsine of sine of pi over 6 is equal to the arcsine of 1/2. In other words, this expression here is the angle whose sine, or I should say the angle in the interval -π/2 to π/2, whose sine is 1/2. Okay, good enough. So let's put up the unit circle. Again, you really need to commit the important angles on the unit circle to memory in order to do this class. So let's put the points where that correspond to the angles whose sine is 1/2. We know as the y part of the coordinate that appears on the unit circle is where the y part of the coordinate gives the sine. So we're looking for a point where the y part is 1/2. We know from remembering the unit circle that that's going to be √3/2. This point here also has a sine of 1/2, and its x value is -√3/2. So there are the 2 points where the sine is 1/2. One of them looks like that. The other angle is going to look like that. But remember that we're only interested in angles that are between -π/2 and π/2. So this is an angle down here of -π/2. This is π/2. The only possible point that we could be interested in is that one. And once again, just from knowing what the angles on the unit circle look like, we know that this is 30 degrees or π/6. So it's from there that we can say that the correct answer is π/6. Now, why does it make a difference that I did it this way? Let me show you. Let's evaluate the arcsine of the sine of 5 pi/4. The naive answer to this is just to say 5 pi over 4, but that's actually not correct, because remember that the arcsine has to give us an angle that's in the interval negative pi over 2 to pi over 2, and this is not. So sine of 5 pi over 4, and if you need the unit circle to do this, you can do that, but that's going to be, let's see, that's pi over 2, pi, 5 pi over 4 takes us there. So this is going to be the point negative root 2 over 2, comma, negative root 2 over 2. Okay, so the sine of 5 pi over 4 is negative root 2 over 2. So what we're looking for is an angle in the interval in the interval negative pi over 2 to pi over 2, whose sine is negative root 2 over 2. So we're looking for, first of all, a negative y value, and we're looking for one down here. It's going to have the same y value as this point does, but it's got to be in the correct interval. So we're looking for this point, and again, just from knowing the unit circle, we know that this is going to be, positive root 2 over 2, because we're now in the positive x-axis, and negative root 2 over 2, because we're in the negative y-axis, and this angle is negative pi over 4. So this is negative pi over 4. So that's how we end up with the equation arcsine of the sine of 5 pi over 4 equals negative pi over 4, because it matters whether the angle that we're given is in the correct interval or not, and you always have to keep that in mind when you're solving these types of problems.